Hi, Dr. Joe. Hi, everyone. I hope you are all doing alright and safe. This is Ravi. In this video, I'll be talking about one of the attacks known as resource freeing attacks. It was introduced by those three guys. None of them is working in the research anymore. They are working at Facebook, and one of them also is working in AWS, and the third one is working in Facebook. So Uh, it was actually introduced in 2012, so let's get started. Our agenda will be as follows. I'll give some introduction and background about this kind of attacks in general, and then I'll get into it what actually is RFA. Then we'll discuss their evaluation on their test bed and also on Amazon AWS EC2. Then we'll talk about discussion and conclusion. So RFA or research for an attack is of those kind of attacks called sidechain attacks. So I'll give some introduction about what actually is sidechain attacks, some examples. Then I'll give some cloud computing observation and assumptions, and we'll talk about the resources that will be uh, used and we'll be discussing in this paper. So what is sidechain attack in general? We may be familiar with those kind of attacks that are dependent on some software bug or cryptanalysis. Someone is trying to exhaustively trying all the keys and break the key. But this kind of attack is different because here uh, we are trying to exploit or use the way the machine component or resources are talking to each other, how they were implemented. So such an attack are any attack based on information gained from the implementation of the computer system itself. It has nothing to do with any weakness in the software or something like this. So those are some kind of or examples of side channel attacks where the power consumption, say if you lost your credit card or someone steal it, is somewhere ways they were able to plug it in a machine and they were able to calculate the power consumption while it's decrypting and encrypting, they might be able to break the key. Another type is called electromagnetic attacks. Say, when the processor is computing something, they have some radiation. So they say that they might be able to break whatever they were doing using this small radiation around the processor. Third type is timing information. And by timing information, say you wanna break your victim password. So you don't know it, but you just try. If the server response to your trials depends too much on the how many character of your password is correct, you might be able to use this information to break the whole code using too much trials. Another type of sidechain attack is called keystroke sound, and this is kinda weird actually, but if you can imagine something, one day one can do it. So this is actually using the keystroke sounds of your keyboard while you're typing, for example, your password. There might be able to break the password and know it. Another type is cache attack, which is of great interest nowadays. And even the last one, as far as I know, was in 2017. It hit Intel processors. It's called Meltdown and Spectra. And I remember at this time, Intel published its solution or patch for this problem, but unfortunately, they said you might lose like 30% of your processing power. So I'll give some just few facts about cloud computing here. So cloud computing actually provides high efficiency by multiplexing multiple customer workloads onto a single physical machine instead of have just one server or one application per physical machine. With cloud computing and virtualization, you will be able to have multiple application or operating system running on the same physical machine, which achieve high efficiency and high utilization of your resources. But unfortunately, this comes at a cost of that if two customer applications share the same machine, they might contend for the resources. And this is because current virtualization hypervisors do not provide 100% isolation between the resources. So we have some assumptions here that every application will have just one bottleneck resource. You have some applications that is bottlenecked by the CPU. You have some applications that's bottlenecked by the cache. And by bottleneck, I mean if you were able to increase, for example, say we have our applications that is network, its bottleneck is the network. If you were able to increase the network, that will make the application faster. On the same way, if you have another application that's CPU bottleneck, if you are able to increase the bottleneck resource, you will be able to make the application faster. So here we assume that every application have only one bottleneck resource. So even for the same application, depends on the type or the content you are serving, you might have different bottleneck. For example, if you have a web server, if this web server is serving static content, most probably it will be the bottleneck will be the network. If it's serving dynamic content, it will be the CPU. So these two facts actually are important in our attack of today, because in RFA, RFA leverages these observations to improve the VM performance by forcing a competing VM. We say that the resources will be competed by different VMs. So the VM performance, you can improve the VM performance by forcing a competing VM to saturate some of the victim bottlenecks, as we will see later. So here I'll be talking a little bit about the resources that we will be dealing with. So I just need to say some facts about this scheduler. They will be using ZenCitrix hypervisor, and also the other experiment will be in on EC2 AWS, which both of them are using this specific hypervisor. This hypervisor is using a scheduler called Credit Scheduler. So first of all, what's a scheduler? Scheduler is this software or piece of software that is required to determine which virtual CPU should be run on each physical CPU at any time. You have two virtual machine running on a physical machine. You need to assign each virtual machine which has virtual CPU to be running on a physical CPU. This is the task of a scheduler. Here our credit scheduler have two mode of operation, one fair share allocation, where every virtual CPU takes the same amount of time or the same share, while the other type is low latency dispatch. And this mainly used for I/O intensive VMs because they usually use the CPU for less time. So you just want to give them priority. So if they need the CPU, you just get it. They just get it. So the scheduler gives the virtual CPU credits at a predetermined. This is how the scheduler is working. The scheduler is giving every virtual CPU some credits or shares of the CPU, typically at every 30 milliseconds. Then, every 10 milliseconds, a periodic tick removes the credits from the currently running virtual CPU. Once virtual CPU is running out of credits, so it will be preempted and the next virtual CPU in the queue will be using the CPU. So we have two different modes of operation for this credit scheduler. It's kind of trade-off between performance and efficiency. What's your goal? Do you want to keep your processor working all the time? If so, then use work conserving mode, because here you allow, if you have one virtual machine that is in ideal state and don't use and doesn't use its allocation, another machine can use it. So it achieves high efficiency, but unfortunately with low performance isolation. The other mode is the opposite, which is non-work conserving mode. This is you give every virtual machine a minimum amount that even if it's not using, no one else can use it. But this comes with a reduced efficiency and it will improve the performance isolation. Also, if you have multiple cores or multiple CPU on your multiple CPU sockets on your physical machine, you can pin a specific virtual machine to be running only on this core. Or, on the other hand, you can just keep it floating all the cores and sockets you have on your physical machine. Second resource here is the memory, and then achieve isolation in the memory and did good job for this by just giving each VM a static number of pages. It doesn't swap pages to disk. There's a lot of techniques to achieve high utilization of the memory. One of them is swapping. Then use the deduplication to achieve this maximum use of the memory. It doesn't use a swap, it doesn't use ballooning or TBS or this techniques. But unfortunately, all the x86 hardware does not provide the ability to enforce pair virtual CPU limit on memory bandwidth or cache usage. And by memory bandwidth, I mean the rate at which the processor can read or write from the memory. The last resources here we have are the network and the disk. So then try or to achieve fair sharing of the disk and network access by using a round robin order. Round robin, like take the first request, then the second, then the third, and then go back to the first, second, third, and so on and so forth. And for disks, this can lead to wildly varying access time. So they have observation here for EC2, which is a computing machine from Amazon AWS. That EC2 sets caps or capacity limit on the network bandwidth available to an instance at around 300 megabit per second, but it does not cap the disk bandwidth. So for network, you will be having a minimum of 300 megabit per second even if you don't use it. So I mentioned these resources just to give you this important fact that resource isolation is very important in cloud computing field. So if you have perfect performance isolation, it should guarantee that the behavior of one guest virtual machine does not affect the performance of another guest virtual machine that is co-resident on the same physical machine. Also, VMM or the hypervisor currently known are only focused on fair allocation of the CPU and the memory. But there is a lot of other resources that they don't do a good job till now in performing the isolation or achieving the isolation between those resources, like the memory bandwidth or the cache capacity or the network and disk. And this makes the availability to mount some sort of attacks like the one we have for today. So that was the introduction. Let's go into our paper topic of today, which is RFA. So what's RFA? It exactly is resource freeing attack. So as the name implies, you are trying to free some of the resources that usually they will not be free. So the general idea here is that the guest that suffers due to performance interference can affect the workload of other VMs on the same physical server in a way that improves its own performance. And by this I mean if you have two co-resident virtual machine, one is yours and the other is the victim, let's call it victim virtual machine, it because due to the poor isolation, it will badly affect your performance. So if you used this resource-free attack, you might be able to drive it to some bottleneck so that you can free the resource that you are of interest. Like for example, if you are cache intensive, you can drive the other machine CPU up till you free the cache. We'll see later in more detail. But to achieve this, you need to achieve coincidence. You need to know that the victim are on the same virtual machine of yours. And also the victim machine needs to be running some sort of public network service so that you can reach it. And this is actually achievable. For example, Amazon has 25% of their IP addresses available publicly. They are running some web servers. So our attack will consist of four parts or three parts. Uh, the first part is the victim, which is the machines that we will be trying to consume its resources. The second is a beneficiary, which is the greedy user or the greedy machines that want to use someone else's resources, and the helper. And the helper is a machine, virtual machine, or software application that will help us to achieve this. So the helper will be actually trying to achieve the beneficiary goal, trying to drive up its some of its resource to its bottleneck, so that the beneficiary can make use of the other resource. And these are some kind of ways on how to modify the resource consumption of the victim. For example, the helper. Think about the helper right now as a software. So the helper may submit some CPU intensive requests for dynamic data that drive up the server CPU usage until it exceeds its credit limit and is preempted by the hypervisor. We talked just in a minute before that the scheduler will give every virtual CPU some credits, and once those credits are finished, they will be preempted and wait for another 30 milliseconds. Another way is for the helper to request unpopular content, which will skew the web server resource usage away from the CPU towards the disk. Also, the helper can introduce unnecessary disk requests that will degrade the victim disk performance and cause the disk to be the bottleneck. Also, the helper could slow the victim by introducing additional network traffic that makes network bandwidth a bottleneck for the server. So again, the idea here is that we have a victim located in the same physical machine of our virtual machine, and it is badly affecting our performance of the machine because of the poor isolation. So we are trying to drive one of its resources up so that we can take benefit of the resource of interest. So now we will see how they achieved this on two experiments. The first one is on a test bed. They created, think about it like a lab environment. And the second experiment they did was on Amazon AWS, just to make sure that their experiment or their attack is achievable. They can mount it on a real life or real environment. So the test beds I used are based on Zen Citrix, which is open source hypervisor. And I just want to mention here just two information about the Zen Citrix. They are using the concept of DOM0 and DOM-U. And DOM0 is just a virtual machine that is responsible for all the management tasks required by a hypervisor, plus it manages all the physical resource drivers. So they are using this specs. This is version 4.11. I think the last version now is 7 or 8. And as we talked before, they are using the credit scheduler and these resources and specs. So here to simulate workloads, we can use some sort of software to achieve or to put some more intensive on specific resource. For example, now we want to create a workload that is intensively using the CPU. You can just create some software that solve some puzzles like the n-queen problem for different n. Here they are using n equal 14. If you want to create a workload that is intensively using the cache, you can use something called LLC probe. It will be probing the cache of the machine in a way that will drive it up, and so on and so forth. So all these are just like some sort of workloads to achieve some or put some uh, intensive workload on a specific resource. And we can execute each workloads here means like the virtual machine that is running this software that will affect the specific resource. So here we can run every virtual machine in 3 different modes according to our need. For example, you can run, if you have 2 virtual machines, you can run both of them on the same core. They call it pinning. You pin the CPU of this, the virtual CPU of this virtual machine to run on this specific physical core, or you can allow them to float within to float within the same socket. So we have 3 different modes. Some cores time slices to VMs on a single core, or same package run 2 VMs each pinned to a separate core but on the same package. Here, if you have 2 sockets on your motherboard, you can run each virtual machine on different socket. So before mounting your attack, you need to make sure that actually the victim virtual machine has bad effect on you. Otherwise, no need to mount any RFA. So here in this, we can say it like preliminary or intermediate experiment. They are trying to um, study the effect of all the resources on each other. For example, here, say we have our virtual machines that is it happened to be like CPU intensive. Here they are studying the effect of coincidence with a machine that is also CPU intensive. and again the effect on of having the victim virtual machine or the co-resident machine intensively using the network, and so on and so forth. So you are trying the effect of different uh, workloads on your virtual machine. So this is, you can think about it like the effect of the poor isolation between the resources you have. So, and it turns out that if you notice here, regardless if you are using your configuration in the same core, or you're running your virtual machine on the same package, or you are running your virtual machine on different package, turns out to be the network the network has the very bad effect on the cache. And CPU and memory has very less interference between each other, which means that the hypervisor is doing a very good job in the isolation. But again, the network has the worst effect on the cache. LLC means the last layer cache. You know, if a processor now is using three cache layers, the layer 1, 2, and 3. LLC is the last layer and is shared between all the cores within this socket. So because network has the worst effect on LLC, that will be uh, the resources that of interest during their experiment. And the degradation caused by the network on the LLC is caused by those reasons. That the HTTP request cause frequent interrupts and hence frequent preemption due to boost. And boost is just, as we said before, we have fair sharing and uh, some sort of priority. We are giving the high intensive input-out machines a priority to use the CPU. So if your victim is HTTP or web server, and every time it gets some requests, it will preempt your workload and will be using the CPU and the cache. This will pollute your cache, so it will take longer time to achieve its tasks. Also, in the same core and same package configuration, the web server itself will run frequently and displays the cache content, which will increase the misses and reduce the hits, so it will get you bad performance. Also, in case of running on different sockets or allowing your virtual machine to float through all the CPUs you have, your virtual machine might happen to interfere with the dumb zero machine. And we said dumb zero is like, think about it like the management virtual machine. So it will also be interfering with your virtual machine, make some bad performance. So here we said that we have our attack consists of the beneficiary, the victim, and the helper. So the beneficiary here will be a machine running some cache-bounded program like the LLC probe. This is just a probe or application that will put some load on your cache. The victim will be a web server that's running or serving some static and dynamic content. The helper will be the same as like a load generator, but it will request some CGI scripts to just to simulate like dynamic content. So we said that the web server serving static content and dynamic content. So the helper will be requesting the dynamic content, which is represented by this CGI scripts, and the legate traffic to the web server, which is representing the normal case, will be simulated by some load generator that will request the static content. So again, we have our web server serving static and dynamic content. Static content will be used to simulate the legate traffic, and the dynamic content will be used to simulate the uh, dynamic content. So this is how they did the experiment. First, we have our victim serving the web requested from the generator at different rates at 0, which represents the ideal situation where the server is just sitting do nothing, and then start to increase the rate. And at each rate of the web server, we are calculating our LLC and calculating the runtime. Here, when the victim was idle, our server ran at 4000. Once we increase the rate, then the performance start to getting worse. So the server is now taking more time, then more time, more time. So the time is increasing with the increase of the request rate. So this column represents the degradation caused by the victim correspondent with our machine. Here, this is the same situation, but in the case of a floating core where you allow the virtual machine to run on every core on the physical machine. So if you notice, it represents the same trend. There is a degradation also with the increasing of the number of requests, but it's a little bit better than this. And the reason for this is that sometimes, sorry, the reason is that sometimes the victim and beneficiary do not share the cache because, as we said, the machines are allowed to run on every virtual machine, on every CPU, core, or socket. So sometimes they don't share the cache, so the victim will not have that much effect on the beneficiary. So this is the situation now. We have the beneficiary performance degraded as we have just seen, and this degradation is caused by the victim frequently preempting the beneficiary and thereby polluting its cache because it's serving web requests. Every time it gets a request, it will preempt the beneficiary and use the cache and polluting the cache. So now our attack aims to exploit the victim's CPU allotment and as a bottleneck resource in order to reduce the number of requests it serves. So we'll be trying to get the victim CPU to go up so that it can be able to only serve a small number of requests. So now let's see how the attack will be implemented. So the helper will introduce some CGI requests. We say that CGI request is like just represent the dynamic content of the web server, and this will push the CPU up of the victim, and this will finally achieve like making the web server only able to serve a small number of requests. As we talked before in congestion, once you overwhelm a server with some requests, it will the sender or the receiver or the web server will request the sender to slow down so that it's not overwhelming. So this is the case now. We're trying to drive the CPU up so that we can get the server only serving a few number of requests. And that is the evaluation of the test bed here. We have it for one time for same core, and here on the graph at the right, this is the same experiment but with floating case where the VMs are allowed to run on every core. So here the orange here represent the no RFA. This is where the our request rate for the RFA or the helper requesting or running the CGI at 0 rate. And the green one here represents the baseline. And the baseline, I mean, where the server is, the victim is sitting there doing nothing. So, and the blue and and this 161.320 represents the RFA request rate. So, in brief, this green represents ideal, where the request rate is 0, not 1000. Here, this represents our request rate of the RFA is 0. Here's the orange one. And those in between represent different request rate like 160, 320, and so on. So our goal here is to getting closer to the ideal case. If you get too much closer to this ideal case, it represents as if you negate the effect of the victim at all, as if you just sitting alone on the machine. So as we can see here, the RFA give us some benefit. Instead of being run at the LLC being run at 1000 or 10,000 microsecond, it will only be running, for example, at like less than 6,000. So this is the benefit of running RFA. Here also, situation is the same, but we are running on the floating configuration. So we can notice here also sometimes that introducing RFA will sometimes hurt the performance, as we can see here. And the reason for this is that, as we said before, that sometimes the beneficiary machine will be running on the same core or the same socket as the DOM0 machine, which makes some interference act as a victim too. So this sometimes hurts the performance, as we can see here. So this is what we just said here. So to negate the effect of the DOM0 in the case of the floating configuration, the only way to do this is by indirectly saturating the web browser and hence reducing the rate of incoming requests to the web server. As you can see here, this represents the offered web server request rate. This is the requests at the load generator side, and this is the requested that is actually served by our web server or our victim. Here, if you can see, by introducing this RFA, we are reducing the ability of the server to reply to the web requests. Here, you need the load generator or the sender has 3,000 requests, but the server was not able to serve more than, for example, 2,000 at the RFA request of 320. So here is the same situation here, but they are running different workbenches or benchmarks. Sorry. So before, in the previous experiment, they just used the LLC experiment. Those are some other benchmarks like the LLC, but they are different standards. So they run the same experiment here, and from what we see here is that always the RFA like 320 or 640, they always achieve some benefits. Here, the longer the bar, the better, because here we are calculating the normalized performance, which means it's calculated by T dash over T, where T dash is the running time of the LLC, the running time of the workbench, while the T is only the running time at the ideal case, as there is no request rate at all. So the longer, that means that we are closer to the ideal situation. So this is the longer the better. So we are able to achieve like some performance improvement like 3.4 in case of 640 RFA. And all these experiments were actually running at request rate by the load generator at 3,000 requests per second, which represents the legitimate metric. So that was the evaluation on the test bed. Now we are evaluating on the EC2, and they requested or they tried to implement this on EC2 because is always real situation are always different from the lab situation. So they were just trying to make sure that their attack is feasible and can be achievable in real life. Also because then or Amazon doesn't publish their configuration, so maybe Amazon has already prevented this RFA, so they wanted to make sure that they still able to implement this uh, RFA. But in the test bed, this is your machines and you have full control. You can put this machine with this machine. But in case of EC2, you don't have full control. You just request a virtual machine, and Amazon is responsible to put it somewhere on their data center. So, but to achieve this RFA, as we said before, we need to achieve the core is done. How can we do this in an environment, public environment like Amazon, that we don't have full control? That's actually another paper that will be presented by one of other colleagues, but I'll just give like some hints about how did they achieve this. So the attacker can scan nearby internal IP addresses on appropriate ports to see if there exists a public network services. For example, if you requested an instance and you got an IP like .1, you can scan .2 on port 80 or port 8080 just to make sure or to verify if you have any public services nearby you. Also, they used like the round trip times to confirm if they correspond with the machine or not. And also in the other paper they implemented, they were able to come to a fact that all the neighbor's machine will not be far than you by 8 IPs. For example, you got .1, the machines that resident with you or correspond with you on the same physical machine will not be far than 8. So they will be either take .2, .3, .4, not more than 8. So they launched a large number of instances, and here they are trying to achieve coincidence. So they launch this large number of instances, and they check the coincidence using um, the round trip time and the covered cache paths cover the channel. And cover the channel is to having two processes that are not supposed to talk to each other, but you are able to, by using this cover the channel, you are able to have them talking to each other. And there is a paper called Hello from the Other World, for those who might be interested. They were able to like install or implement SSH channel through the cache. So here they are using the covered, or they use the covered channel to confirm that the machines are correspondent to each other. So this is the results. For example, this machine 1 has 4 instances. This machine 2 has 2 instances on the same machine. And definitely those machines are all under their accounts and their control. But the physical machine itself might have different uh, instances for different customers which are not under control, which will represent the noise as we will see later. So the attack strategy is the same as before. They run those benchmarks on the physical machine. So for example, here selected, say this machine has 2 instance cores. They run on one of them. One of them will represent the beneficiary, and the other will represent the victim. And they run the helper on another physical machine. And then they calculated also the normalized performance using T dash over T. And T as we said, represents the baseline where there's no request rate at all. And T dash represents the specific request rate, for example, 2000 or 3000. And here's the results. As you can see here, always the RFA situation is getting us better performance here. Also, the performance is not that much, but we still can achieve like 6% improvement here in the case of LLC Pro. We'll always notice that always the workloads that is cache bottlenecked will always get better performance with RFA, using RFA. So now we will go to the discussion and conclusion. So although we're able to implement this RFA in real environment like Amazon, there's some challenges we still need to work on. Like for example, may be difficult to predictably modify the victim workload because the victim's normal workload may be unknown to the attacker. Also, it may be that the correspondent instance do not have services that are accessible to RFA. You need to access the victim, right? But what if your victim do not provide any public service like web service? You cannot implement this unless you use some other attack like try to access the disk instead of the network because it's not publicly available. Also, the client workload we experimented with does not reflect all victim workloads seen in practice. Say, for example, the workload that corresponded with you was not a web server, so we have different workload types. Also, you need to take into consideration the cost you need to pay to implement this attacks. For example, now to have the helper running, you need to have an instance for it and you need to pay it. So you need to make sure that the amount you pay worth it. So how to prevent the RFA? To prevent RFA, you can just run your server in a dedicated physical machine. You don't want any other customer to be correspondent with you, but you need to pay for it. It's much more. Also, if the hypervisor was able to achieve 100% isolation, that would prevent RFA. Or you can just apply a smarter scheduling, if any exists, where the hypervisor detects the workload with conflicting resources and scheduling them at different times so they do not concurrently share the contended resource, or on separate core or package to reduce contention, as in the case of the last level cache. Also, if you can detect this kind of attack, RFA attacks, and prevent them, that would be perfect. But unfortunately, this is not the case because you will need to prevent some legged traffic to do this. So the conclusion here is that performance isolation proves an elusive goal in cloud computing environment. Current cloud providers, hypervisors, do not provide strong isolation for reasons of cost and efficiency. As we have just seen, experimental RFA are feasible. It can be implemented in real life. Also, RFAs are a problem for both the direct victim that incur increased cost due to surprise requests, and also for the cloud provider, which loses overall efficiency because of the load caused by the malicious gaming of resource allocation. That was it. I'd like to thank you. I hope that was informative for you, and thank you.